Welcome ENET 130 Semiconductors at Bellingham Technical College. This is our sixth main lecture recording in our course on semiconductor materials and devices and circuits. And in our last lecture we dealt with diode use for half-wave rectification. So we looked at using the one-way current flow action or capability of a diode to basically take just the upper, or depending on how we orient it in the circuit, just the lower half of a periodic, a neutrally, a no DC offset periodic waveform. And then we looked at ways to smooth that out and give us closer to true DC using a capacitor in parallel with our load. And we looked at using the tau time constant of our capacitor load circuit to basically gauge what size capacitor we needed. And we explored the difference based on the size of our load resistor and capacitor of our true DC and our ripple, our remaining periodic signal superimposed on our DC. And we admitted that there were some limitations. No matter how large of a capacitor we used, it seemed that we always had a bit of ripple. Well, one way to make the ripple smaller and get us closer to true DC is to stop throwing away half of our input waveform. And the way we do that is to use additional diodes and achieve what we call full wave rectification. So what that means is effectively we're going to shift the flow of current coming out of our transformer secondary such that we take both the positive and the negative half cycles, but we shift those relative to ground such that they both flow through the load in the same way. So we can think of our diodes as basically being one-way valves that are redirecting current that flows alternately in two different directions and redirecting it around. So at the end of the day at the load, it's always coming in the same direction. So in that way we capture the entire waveform. So there are two main ways to achieve this, and it's basically differing by the type of transformer we have. The first is shown here in Mr. Fiore's figure 3.12, and that's called the center tap full wave rectifier. And the center tap refers to the transformer here. So in our transformer we have our primary coil where our primary signal is coming in from a generator or from the wall, and then our secondary, which has now stepped that voltage from the primary up or down, or kept it the same and just provided electrical isolation. You can do any one of the three. And rather than just having, the positive end polarity effectively for going with the forward half cycle, and then the negative, we've put a grounding point, a center point, so we have another tap. Theoretically this could go out to another circuit, but for the point of view of the rectifier we've grounded the center tap. So basically our secondary waveform, when it goes full positive at the high point of our forward cycle, we're going to have our positive voltage being seen up here at one end of our coil. We have 0 in the middle, and then we'll have negative at this end. And because we can only have the full secondary voltage over the full coil, what we'll be doing is splitting that and centering it. So if, for instance, our secondary peak voltage was supposed to be 12 volts, so that's amplitude, one peak was 12 volts, we would have 0 here in the middle, and we'd have +6 and -6. So a total of 12 over the whole coil, and split evenly in the middle, because ground is always our 0 voltage reference. So if we want to step our way through this, we can think of our positive half cycle giving us a positive voltage here at our polarity dot for our transformer, which indicates a conventional current is going to flow out of this end of the coil. It's going to flow through this diode after losing the forward bias voltage necessary to go through it. And because these are typically silicon rectifying diodes, we'll assume that's 0.6. So we had half of our secondary transformer voltage coming out, losing 0.7 volts, 0.7, not 0.6. We get to this node, and at this point our conventional current has a choice. We have a parallel circuit here, a node, so it can either flow on to our output circuit, or it can flow down here and through this other diode. And because it's conventional current, it's positive current flow, it's not going to go through this diode. So this diode's going to act like an open, so it's not going to go down this vertical branch. It's going to continue on to our output circuit, and it is going to simultaneously charge our smoothing capacitor and drop over our load. And depending on how big our smoothing capacitor is in our load, we'll get a certain amount of smoothing. Okay, meanwhile, 1/2 period of time elapses, and now we've got our positive current flowing out of the other side of the transformer secondary. So now we're looking at our negative half cycle. That's the one we threw away with a half-wave rectifier. Okay, so and at this point we would have effectively negative conventional current flowing through D1, but it's easier to think about regular positive conventional current now flowing through the other side of the transformer secondary. So we're at the negative half cycle. So conventional current flows through D2 and comes back up to the same node, and now it has a choice. Positive current could flow, it could try to flow back through the diode, but it can't because the diode is now reverse biased, so it acts like an open. So again, it has no choice but to flow the same way to the output circuit, continue to charge the capacitor and flow through the load. And back we are, one full wave cycle. So we now have current charging the capacitor and flowing through the load across both cycles of our transformer secondary. The only thing that we're giving up at the load is effectively we are going to reduce our peak voltage by half of what the total transformer secondary is, and then we're going to subtract 0.7 volts for our forward bias going through each diode. We go through only one to go through the load, but we do have to take that toll. Okay, so let's look at an idealized output here in figure 313. So if the blue was 1/2 of our transformer secondary total, so our ground to one end of the coil, if our blue input was there, we would have over the load the green, and that would be obviously with no smoothing. So instead of only having one hump and then no voltage and then another forward cycle hump and no voltage, now we are getting basically a half cycle every time. And another thing we can notice is we just increased our frequency, because we now have a waveform that is defined by just this sort of positive set of camel humps, if you want to call it so. So one waveform is no longer the sinusoidal up and down, it's just the half. So we've now completed a single waveform of the green curve here at this point. So at the point where we would have, at the time elapsed for a single sinusoidal waveform of our transformer secondary, we've now had two waveforms of the signal going across our load. So that's important to remember if we're going to do any frequency dependent processing or power calculations using our vector algebra that we used in AC. We've had a frequency change, so we don't want to go mixing up our transformer secondary signal and trying to apply Pythagorean or those other algebraic manipulations to the green curve, because the frequencies aren't the same. And there are other ways to deal with that we learned in AC. Okay, let's take a look at that in TINA. So we can construct a a complete center tap transformer full wave rectifier in TINA. TINA has transformers we can select, and this one is the center tapped transformer. Coupled transformers, you have a choice here. You can use an ideal transformer with a center tap. So it looks like that. So you can choose one of those, And you can choose your number of input coils and your total output, and then it'll split that evenly between N2 and N3, because that's what center means. The tap is at the center there. So on this circuit, we've got a sinusoidal input into our primary of 2 volts at 60 hertz. And let's see what our ratio is on our transformer parameters. Oh, excuse me. This is the ratio. So this is the ratio by definition secondary to primary. So we should be increasing our voltage output by a factor of 6. So we would expect 6 volts total from our node A to our node C. Flipping polarity. We have our rectifying diodes, and here's our load. We're not going to look at a smoothing capacitor in this case because it's a little bit easier to see what's going on without that. And we have measurement points at A, B, and C, and at D and E, so we can get our load voltage, which is what we really care about. And we've copied what Mr. Fiore has. He grounded his center tap of his transformer and his load. And that does make it a little bit easier for the simulator to define things in the positive. Otherwise, you end up getting your signal across the load in the negative if you don't ground this. A note of caution is just a little reference back to transformers. By grounding our load, or by grounding the center tap and having a grounded primary, we just lost our isolation. So unfortunately, because ground is ground, if there were any stray currents, they could basically communicate through the earth ground. So just as a note, these grounds don't both have to be there, because this is an isolated transformer. So if we didn't want anything on this side of the circuit talking to the primary, we would take away one of the grounds. But we don't need to for this simulation, so we're going to leave them there because it makes it easier to look at our reference voltages. So we got a reference voltage at center and positive and negative, or both polarities of our transformer secondary, and across our load. Now, just as a caution, we have a second rectifier circuit here, and all of its input points are going to come up when we do our transient analysis, but we're just going to get rid of them real quick so they don't clutter. 60 cycles, so we're going to use 20 milliseconds to give us 1 or 2 full wave periods so we can really see what's going on. Tina gives us a bunch of warnings that we do have some test points that are floating that aren't grounded, and a lot of those are in our second rectifier circuit where we don't have everything grounded. We've kept it isolated, but that's not a problem. It's not an error in our circuit. So we're going to pick the curves we care about. We've got voltage measurement nodes D and E over our load, and A, B, and C at our transformer secondary. We don't really need to see the primaries, although we could at first. Let's start with that actually. Let's walk our way across our circuit. So this is a measure of our transformer secondary output across the whole secondary coil versus our V source, which is our primary voltage input. So you can really see here what our transformer is doing for us. This is definitely a step-up transformer. So the gray curve is our primary voltage input. So there's 2 volts peak, and by comparison, our secondary is giving us about 12. So it really was an N ratio of 6. So it's a 6-to-1. So our transformer is doing exactly what we want it to do for us. So that's a good check. All kinds of things we can check with our simulators. So we're not going to display the primary input anymore. So now let's just check and see what we have going over our load. We kind of know what point B is. It's at ground. So now let's look at our load voltage, and we'll see what our rectifier did for us. And I always like to display the legend so I can see what the curves are. And point E, I'm going to make this a completely different color so it's easy to tell. Okay, we've grounded point E And so our secondary tap, because E and B are connected, so these are grounded just like in Mr. Fiore's picture. So E stays at 0 all the time because we grounded it. So here's our secondary, transformer secondary signal, and you can see that with the exception of these little lags for the 0.7 volts going over the diode, our green curve is our load voltage output, so we're really capturing the entire waveform, and so it's all now in the positive. So we have pulsating DC going across our load. And just to verify that we should have 6 volts peak minus the 0.7-ish going through our diode. So you can see that here in our peak that we're measuring. That's pretty close. Again, our model is probably giving us a little bit non-ideal or behavior for our diode, so we have 6 minus a bit for the forward voltage of the diode. So that's reasonable. So there's what we get with a center tapped full wave rectifier. So if we needed to choose a capacitor to smooth this, we'd be smoothing between this peak and this peak and wouldn't have to go all the way over to this peak over here. So we could have a much smaller capacitor resistor, a much smaller tau, and still get a nice smoothing. So we just made our job much easier. So that's center tapped. Okay, pretty nice. You have to have a center tap transformer. What's the big deficit? You're reducing your secondary transformer secondary voltage by definition. You can really only take half of it. So you've got that reduction in voltage. So you've got to size up your transformer if you have a certain load voltage requirement on the output. Okay, what if you don't want that to happen? What if you want to be able to see your full transformer secondary voltage over your load, maybe minus what you have to drop to get across the diodes? If you want to do that and get full wave rectification, you use what's called a bridge rectifier. And this is shown here in figure 3.14. So we have, again, transformer, we're going to have a primary signal coming in, and so we don't have a center tap on our secondary. We're just going to use the entire secondary. So we've got on the forward cycle, the end of the coil with the dot will be giving us a positive voltage source. Conventional current flows out. So if our secondary, say our secondary voltage is 12 volts, we'd be going between 12 and 0 effectively. We don't have that 0 point in the middle necessarily. So on the forward cycle, we'd have conventional current flowing out of the dotted end of our transformer and into the bridge. So let's scale this up as we trace the path of our current through with our mouse. So we're at this point at the 12 o'clock position on our bridge. So conventional current is not going to go through this diode because it's reverse bias. It's going to go through D2, not through D1, and it's going to hit this point in the circuit, and it can't flow through D4 because that's reverse biased. So it flows out to the output circuit, charges the smoothing capacitor, and flows through the load. And it flows through the load and back into the bridge, and goes back down through D3. The diode D1 at this point would be forward biased, but it's not going to flow back uphill into the transformer secondary because it's dropped voltage. So that would be flowing uphill up the voltage gradient effectively. So it's going to flow through D3, which is forward biased and effectively in the downhill direction of voltage gradient, and then back into the back end of the secondary. On the negative half cycle, we have basically flipped the polarity of our secondary coil. So we have conventional current flowing out of the bottom end of the coil, positive current flowing out of the bottom. Conventional, we have a reverse happening. Conventional current flows up to the node between D3 and D4, can't go through D3, goes through D4, can't go through D2, reverse bias again. It goes out to the external circuit, comes back, and This time the downhill gradient is through D1 and it flows back through. So it's a little bit easier to see on Mr. Fiore's color-coded pictures. Very good. So this is our forward cycle. You can see the path of the current out of the transformer secondary. Conventional current flows through D2, through the load, through D3, and back in. And in the negative half cycle, here's our path out of the bottom end of the transformer coil through D4, through the load, through D1, and back into the transformer secondary. So one big thing that we noticed, we're using the entire transformer secondary, no center tap flowing in and out. And the other thing we noticed is we're going through 2 diodes each time, which is not a problem if we've got big diodes with a big reverse saturation. We've got something like 20, 30, 50 volts. But if we got something small like 5 volts, that forward bias voltage toll through the diodes can get significant relative to our signal. So if we got a 2-volt signal, we're going to be chopping off something like 1.4, which might get us down into the noise level that we might not want to tolerate. So that's something to be aware of. Those forward bias voltages are material dependent in the diode, and you don't have a lot of choice in what you can do unless you get a different diode. So this would be a great, if you had a small voltage signal that you needed to rectify, this might be a great use for germanium diodes, which have a smaller forward bias voltage, generally 0.3 rather than 0.7. So good thing we have a lot of components. So we can take a quick look at that on Tina. We have our second circuit here, and this is actually a little bit simpler than the center tapped. We're not going to go through the action of our transformer. We'll just take a look at our transformer secondary signal coming in, run our transient here. We have that displayed. So we're going to close out of all the same errors that we saw, or warnings. So this time we're just going to look at T and S, and we will display voltage source 2 with it. Okay, so our voltage source was, we had 5 volts basically coming out peak to peak. So that was our primary. We can take a look at what our step up, step down ratio was. It was a 2, so our transformer secondary should have been giving us 10 basically. So we would expect to see on our peaks on S and T, we would have expected to see something like 10 volts minus about 1.4 a bit. So each of these should be quite a bit less. So we have 9.5 there, and oops, we are not reading the right curve. Your measurement tool is specific to the curve you click it to. So 9.5 and 9.5. We had about a 0.5 volt reflected for our diode forward bias voltage on the diodes we selected for this simulation. So this is pretty accurate. Instead of having one reduction, we're having a reduction on each side. So our total peak to peak is showing that reduction by 2 diodes. So that is making sense for us given the way things are running through our diode bridge. Okay, if we want to get the voltage drop over the load, and we are looking at our 2 measurement points S and T, we can kind of see if we want to turn off our source voltage. We don't need the primary on the transformer. What we're seeing here now is we're seeing the influence of both paths basically. So on the negative cycle, we're basically measuring just T, and on for the positive cycle we're just picking up S. Our load voltage is going to be S minus T, or T minus S. So it's the difference between those two. So if we wanted to plot out the load voltage, we would literally go through and subtract these 2 curves from one another. And when we do that, we're going to get the influence of that second diode in each direction in the form of these this small offset here. So one way we can do curve subtraction or addition is to go to the post processor. And this is a handy tool when we want to get differences in node voltage points. So it's this bunch of waves, little push button. So we push it. And it can be fussy. Sometimes it will run into an error and not want to subtract things. Sometimes you'll display half of the post processor. You can click on more and open up a line edit that lets you select functions that you've plotted, pull them down, select an operation. In this case I'm going to subtract, so I'm going to do S minus T, and it lets you give it a name, so I'm going to call it VLoad. Create. So it created it up here, and I say OK, give me another curve, and now I'm just going to display VLoad without its two subcomponents, and voila, here's my full wave rectification. I should be able to now see the influence of both diodes being dropped. So now we're just at 9. So we said each diode forward bias was dropping about 0.5. So now, given that we had 10 volts coming out of our transformer secondary, we can see that we've dropped now the effect of 2 forward bias voltages. So 0.5 and 0.5 is 1. We're now seeing a peak voltage of 9 instead of 10. And then we are seeing that same effect down here at these little plateaus where the diode forward bias basically cuts the signal off a little bit between. Again, we've got less time between peaks, so our smoothing becomes different, and we also are much closer to the voltage that came out of our secondary. So we had 10 coming out of our secondary. We have 10 minus 2 forward bias voltages now instead of 5 minus 1 forward bias voltage, which we would have had for center tapped. Okay, that is pretty much it for diode rectification. Beyond that, we can do other fancy things. Mr. Fiore goes through basically a second iteration of smoothing capabilities. Full wave bridge with dual outputs. Basically, we can split our output load voltage in two. Instead of having one big resistor, we can ground the middle and then drop half of our voltage over each. We can put a smoothing capacitor over one. We can put a smoothing capacitor over two. The only significantly new concept that we have with rectification is an additional nuance into smoothing, and that's using a Zener diode plus a capacitor instead of just a capacitor by itself. So that's actually taking advantage of two different diode functions in one. Your rectifying diodes basically give you a single polarity pulse DC, and then the Zener and the capacitor work together to give you beautiful smoothing and give you true DC and really reduce your ripple. So we will pick up the Zener regulation of a full bridge rectifier output in the next lecture, and that'll head us into other types of voltage regulation applications for diodes, such as clippers and clampers, which will chop or shift an entire sinusoidal voltage signal or any other periodic voltage signal up or down and pin it to a certain voltage that you care about. So that is it for this lecture. Stay tuned for the next.